Thank you for coming. And first, let me say I feel great honored by receiving this prestigious awards. I'd like to thank people who have helped me in all possible ways, including getting the visa in the last minute to make this trip possible. And thoroughly enjoyed this symposium. And thank Andrew for giving a wonderful talk that set up the best possible stage for my talk. So today I'll talk about topological materials. And let me first say thank the collaborators. So this work, this line of research was done in the last few years with people, theorists, ab initio collaborators, experimentalists. And so in particular, I'd like to thank my mentor, advisor, Charlie Kane, and then some of the students, some of them are in the audience here, Karen Michelli and Eris Burke. And also, I had the good fortune of working with many experimentalists in the last few years at different places. And also, I'd like to thank my co-travelers in this exploration of topological phases of matter, Andrew Bernavik and Xiaoliang Qi. And we all take the topological equivalent passes in this field. Okay, so I'll start talking about some old work in my PhD stage, and then I'll move on to talk about some more recent stuff. Okay, so since my talk is about topological materials, I'll first start from the material aspect. So one can take a very, very simple views of electronic properties of materials using the concept of this local real space construction, such as atomic orbitals or chemical bonds. For example, if we think about sodium chloride, which is a classic example of an ionic insulator. This material is insulating because electron want to get away from the unpaired s orbital of sodium and join the p orbital of chloride to form basically ion of sodium plus and chloride minus. And the energy gap in this insulating state basically comes from atomic energy difference of the s orbital of sodium and the p orbital of chloride. So this is why an ionic insulator is insulating. There's another classic example of a different type of insulator that we call a covalent insulator. Famous example is just diamond or silicon or germanium. So these three materials, they are certainly very, very different, and people obviously use silicon as the basis for semiconductor industry, but don't use diamond. But from a very crude perspective, okay, in the spirit of topology, I'll say carbon, diamond, silicon, germanium are topology equivalent because you can understand their electronic properties through this covalent bonding. So each atom sits in a tetragonal environment. You have sp3 or hybridization, and the hybridized orbitals of neighboring atoms form bonding and anti-bonding states. And you put electrons in the bonding states, which has lower energy. Then the system is insulating. The energy gap in this insulator comes from the energy difference between bonding and anti-bonding orbitals. So this is why we call them covalent insulators. So now this approach I just described is very much chemistry-like. It's very intuitive chemistry like that. However, as physicists, we know that this is not how we teach about theory of solids. One of the triumphs of quantum mechanics in the 20th century is the development of band theory of solids. So in band theory, we describe the electron moving in the periodic potential of the lattice of the underlying atoms as Bloch waves. Okay, so electrons are really not stuck to any particular atom, but instead they are itinerant. They move throughout the entire crystal, at least at low temperature. So in this formalism, we get an insulator when we have a complete field valence bands and completely empty conduction bands, and if there's energy gap separating them, this defines an insulating state. And so you may wonder, now there's two different approaches to understand electronic properties of insulators, the local versus itinerant perspective. Are they equivalent or not? Are they the same or not the same? And on a more fundamental level, this is the same question as asking the particle versus wave duality in quantum mechanics. Should we describe the system as a collection of localized particles, or should we think of an insulator as really formed by waves, by Bloch waves? And although these two different approaches look very different, for most of the solids, in fact, they are equivalent. And the bridge between the two is just something we know very elementary, is Fourier transform. So we will take a Bloch wave, which is labeled by this wave vector k in the Brillouin zone, and we can re-express it as a superposition of the so-called Wannier functions. Or vice versa, we can express Wannier functions as a superposition of the Bloch states. So for most of the simple solids, band insulators, the Wannier functions, they actually resemble, qualitatively resemble the atomic orbitals, S-like or P-like. In particular, these Wannier functions are exponentially localized. Okay, so now you can see with this these concept of Wannier functions, well-behaved Wannier functions, you can see how the itinerant and localized perspective relate to each other, because for a simple band insulator, the ground state can be approximated very well by just the slated determinant of all Bloch states. Okay, we take the slated determinant of Bloch states over the entire Brillouin zone. That's just the same as taking the slated determinant of all the localized Wannier functions, because this Fourier transformation is just a change of basis. Okay, it doesn't change manipulate ground state. And so this reconciles the dilemma and says the two approaches should give me the same answer. But starting from late 1980s, people realized that not all insulators can be understood using either the local or the itinerant picture, but instead, as physicists, we win over chemistry in some sense. There exists non-trivial band insulators in which the local perspective that will fail to describe the system even at the quantitative level. And these were, I think, one of the early example was coming from Professor Haldane. And he described a strange insulating state which is, has a quantum Hall effect. But this quantum Hall effect arises from the band structure instead from the magnetic field. So there's no Landau level of any kind in the system. And instead, the reason that this material is topologically distinct, okay, this model is topologically distinct from an ordinary insulator, is because there's an intrinsic topological invariant of index that Andrew talked about. And this invariant captures the global properties of wave function in the Brillouin zone, so it's a particular tied to the wave description of electrons in periodic potential. And on the other hand, if you take a slated determinant of atomic orbitals, you're guaranteed that this variable n has to be 0. So you would never get a quantum Hall effect in such a system. So a physical manifestation of such non-trivial topological invariant is the appearance of quantized Hall conductance n e squared over h, where n is exactly this topological invariant, okay, which one can compute if one knows all the electron wave functions in the momentum space. And also these quantum Hall states support chiral edge states that is absent in an atomic insulator, either it's ionic type or the covalent type. And as I said, so this example illustrates the breakdown of the local approach in these systems. In fact, if you try to construct Wannier functions using Fourier transform of Bloch states, you'll find these Wannier functions are not exponentially localized. Okay, so they do not by any means resemble atomic orbitals. And so this is the first example where we can have band insulators, quantum Hall type band insulators that are topologically distinct from a conventional insulator. Now, one of the challenge of realizing this quantum Hall insulator is that, as you can see, it still requires a breaking of time reversal symmetry in a macroscopic way, so one needs some kind of ferromagnetism. One also needs itinerant electrons. As I said, this state is fundamentally different from atomic orbitals, state-determinant atomic orbitals. So the magnetism cannot come from localized moment, but instead it has to come from itinerant electrons. And finally, you want these itinerant electrons to form an insulating state instead of a metal. Okay, we are talking about an insulating state. So this is why it has been challenging to find such a state, and why this subject was not did not get enough attention until a few years ago, where topological insulator came. That revived the interest. Okay, so as you heard from Andrew Bernowitz's talk, so the the idea is that when we consider the interplay between topology and the symmetry, this leads to new types of phases. In 2 dimensions, it leads to the quantum spin Hall states, which can be understood as 2 copies of quantum Hall effect. At the simplest level, 2 copies of quantum Hall effect, where a spin up electron is in a which has Hall conductance E squared of h, where the spin down electron has opposite Hall conductance. So the whole system is time reversal invariant. And in such a system, we have spin filtered edge states. Spin up electron moving one way, spin down electron moving the opposite way. And time reversal symmetry guarantees there's no backscattering. That's what leads to the quantized Hall conductance of E squared over h per edge. And there's this ingenious proposal by Bernavik, Hughes, and Zhang that found the first realization of such a state in a physical system, mercury telluride, cadmium telluride quantum wells. And the prediction was soon confirmed by the transport experiment from Molenkamp's group. Okay, so what I will talk about is the question that comes naturally is can these quantum spin Hall states have 3-dimensional analogs? Okay, and if we think of these quantum spin Hall systems as building from quantum Hall systems, then it's very difficult to see how this generalization can be made because we know there's no fundamental quantum Hall state in 3 dimensions. Okay, and instead, let me take a different approach. As we have seen that what makes these topological non-trivial states interesting is because they're gapless degree of freedom on the boundary, gapless excitation on the boundary. So we can ask the question: can there be generalizations of the edge states of the 2-dimensional topological insulator quantum spin Hall states to a 3-dimensional system, to the 2-dimensional surface of a 3-dimensional system? And for this purpose, okay, let me look at the energy momentum dispersion of quantum spin Hall edge states as in energy and momentum space. Okay, so this momentum is momentum parallel to the edge of the sample. So we see there's a conduction in the valence bands. They form a continuum, and inside the band gap, we have conducting states. And I've only drawn half of the Brillouin zone because the other half is a symmetric image of this due to the time reversal symmetry. And you see there's a 1-dimensional Dirac point at one of the time reversal invariant points. Here, in this example, it occurs at k equals 0, but not at k equal pi, the Brillouin zone boundary. Okay, so because this time reversal symmetry, this Dirac point cannot be gapped, so that's why these edge states cannot be removed. This is what makes a quantum spin Hall system different from a trivial insulator. So now let's think about a 3-dimensional system. It has a 2-dimensional surface and the 2-dimensional with a 2-dimensional Brillouin zone. And here there are 4 different high symmetry points where k equal minus k. So at these 4 points, if surface states exist, they must exist in Cramer's pairs. Okay. For a trivial insulator, there's no Dirac points at any of these 4 points, or equivalently, you can attach an additional layer of, let's say, 2D electron gas on the surface. Then that will generate 4 Dirac points, covering all these 4 high symmetry momenta. What is non-trivial would be that, let's say, the example here, if only one, if we have a 3-dimensional material which only shows 1 surface Dirac point at one such high symmetry point. So this will be a non-trivial example. And it turned out this is what the surface state of a 3-dimensional topological insulator is like. Okay, so so with this reasoning, we see that a 3-dimensional topological insulator hosts Dirac Fermion surface states, and if we can further look at the spin texture of these Dirac points, so if we expand the Hamiltonian describing the surface in the vicinity of these Dirac points, we find that to lowest order in perturbation theory, we can write down a term that couples linear to momentum and to the electron spin. Okay, because on the time reversal symmetry, momentum changes sign, electron changes velocity on the time reversal, and the electron spin also changes because spin is angular momentum, so it also changes sign. So this combination would be time reversal invariant. So from this, we can see that there's a linear dispersion forming at the surface. Okay, so this is the Dirac Fermion surface states of topological insulator. And you have seen many by now this also shows up in graphene, but the fundamental difference here is that the S that appears in this theory are referring to the electron's spin, really to the electron spin instead of the pseudo spin as in graphene. Okay, so these 3D topological insulators provide a rare realization of topological phases in 3 dimensions that goes beyond the doubled quantum Hall states. Okay, so the next question would be, can we find such a topological insulators, 3-dimensional topological insulators in real materials? And so what is physical root to this? And so I'll describe a approach to obtain a topological insulator starting from a trivial insulator. Okay, so this mechanism, as you heard from Andres, in the context of 2D quantum spin Hall systems, is a phenomenon that's known as band inversion. So the idea is the following: that we know that topology can only change via gap closing transition. Okay, topology is a discrete quantity, so the only way it can change is when the energy gap closes, so that the ground state is no longer well defined. Okay, and it turned out that if you want to think about the possible gap closing transition in band insulators in the presence of time reversal symmetry, it's actually complicated. Okay, but if the system has an additional inversion symmetry, okay, where I change all the coordinates x, y, z to to minus x minus y minus z, if the inversion symmetry is present in the system, this gap closing transition becomes very simple. And basically, if you look at the high symmetry points where k and minus k are the same, for example, at kx, ky, kz equals 0, you can label the all the band eigenstates by the parity plus or minus. Okay, and if I imagine tuning a physical parameter such as pressure, strain, or alloy composition, because the states have different symmetry quantum numbers, they do not feel any level of repulsion, and that's why the band gap can close by tuning just one parameter, and then gap reopens. Okay, this does not happen for generic momentum k because of level of repulsion, but inversion symmetry guarantees that no such level of repulsion exists at these special momentum. Okay, and so this kind of a level crossing in the band insulator is what we call band inversion, and this band inversion, as we said, will lead to a change of topology. So this provides a route to change a trivial insulator to a topological insulator and vice versa. Okay, so this change of topology is described by this band inversion process. One can look at this more quantitatively, and in order to describe the low energy theory near this band inversion point, there's a universal Dirac Hamiltonian, and this arises in the following way. If we want to include the conduction and valence bands, which are involved in this band inversion process, that gives us in total 4 different states: 2 from the conduction band and 2 from the valence band, because each of them are spin degenerate. Okay, so one can write down all possible Hamiltonians involving 4 different states as a function of k, and there's a neat way of organizing 4x4 matrices, 4x4 emission matrices, according to the Dirac gamma matrices. Okay, one can use gamma 0 to gamma 4, the 5 Dirac gamma matrices, as well as the commutator between these Dirac gamma matrices. And if we fix the form of the parity operator and time reversal operator, then the symmetry requirement that the system is both time reversal and parity invariant sets severe constraints. So the Hamiltonian is essentially fixed. Okay, up to some unimportant unitary transformations is fixed by this form. Okay, it's given by essentially a 3-dimensional 4-component Dirac fermion, the same as what we have in quantum electrodynamics. And so in this description, the parity switch between the different energy bands is exactly corresponds to the sign change of the Dirac mass. Okay, so when m changes to minus m, the dispersion is the same. So just by looking at the band structure, one couldn't tell. But this change of the mass really involves a change of topology. So it's a small change, but with leads to a big difference. And as you heard from the previous talk, one can also understand the topological insulator surface states using this method. So I can think of the surface of topological insulator, which is the interface with vacuum, as being a topological equivalent to a mass domain wall, where I replace a vacuum by a trivial insulator in which the Dirac mass is positive, let's say. And this domain wall problem is well known in high energy physics in various forms. And if I have a domain wall where mass changes from negative to positive on the two sides, one get a two-dimensional massless Dirac fermions right at this interface. And this can be just obtained by solving this first-order differential equation, where now the mass is x-dependent in this direction, and the kx is being replaced by the derivative with respect to x. Okay, so the explicit solution can be obtained when one can literally see these Dirac fermion surface states. Okay, so let's now try to apply this this procedure to real materials. Okay, so I'm going to talk about topological materials. Here are two closely related compounds that are known to have a band inversion transition. So one is bismuth, the other is antimony. So the reason that people know this transition is because this alloy, bismuth antimony, exists in the whole range of alloy composition. Okay, they do not they mix uniformly with each other. And so this is the ab initio calculation for the band structure of bismuth, and the other is for antimony. And you can see that if I zooming in at low energy, these states form massive Dirac fermions. So in the case of bismuth, the mass is so small that you can't even see it. For antimony, this is much larger. So this has been measured, okay, for the band structure of the alloy has been measured by various techniques to a very, very high degree of accuracy. And people know that when the composition of bismuth is 9%, the gap closes and then reopens. Okay, so this is a realization of the band inversion. But now you face a question: which one of the two materials is topologically non-trivial? Is it bismuth or is it antimony? Okay, so how can we tell? Okay, so so this illustrates, generally, okay, the challenge, which is the change of topology can be deduced from low energy theory of the gap closing transition or the band inversion, but in order to infer topology, we need a reference point. Okay, so the absolute value topology itself can only be determined from the property of wave function in the Brillouin zone. Just looking at the band structure, we couldn't tell. So, or in other words, what we really need is topological invariant. Okay, the topological state is defined by topological invariant, which is expressed in terms of electron wave functions over the Brillouin zone. So how do we now find such invariant? So this is in the summer of 2006, there's 3 different groups, including us, attacking this problem using different approaches, different methods. So the first paper came from Joe Moore and Leon Balance. They used a mathematical approach called a homotopy group to classify time reversal invariant band structures in 3 dimensions. And 2 weeks later, we derived explicit formula for these invariants and construct explicit models for realizing different topological phases. Moreover, let me describe, first that it was so in the 3-dimensional time reversal topological insulators are classified by 4 different invariants, and each of these invariants take 2 possible values, so 0 and 1. So it's binary. It's called Z2. So these 4 invariants can be divided into 2 types. One of the index nu0 is called a strong index. The other 3, nu1, nu2, nu3, together can form a vector, which is what we call a weak index. And so the meaning of these invariants is actually very transparent from the perspective of band inversion. So when nu0 equal 1, we have a what we call a strong topological insulator. And in these materials, they are obtained from a trivial insulator by a single band inversion at momentum, which is given by the weak indices, nu1, nu2, nu3 times pi over a. Okay? For example, if nu1, nu2, nu3 are all 0, and nu0 is equal to 1, such a strong topological insulator can be obtained from a trivial insulator by band inversion just at the center of the Brillouin zone gamma. Okay? And in these strong topological insulators, the surface states have an odd number of Dirac cones, and these Dirac cones are located exactly at the projection of these weak indices onto the surface of the Brillouin zone. So it's got cut off here. But if, for example, if you look at a 001 surface, okay, of this three-dimensional topological insulator, and if band inversion occurs at this point, it will show up at kx equal 0, ky equal pi on the surface Brillouin zone. Okay, so not only the number of Dirac points on the surface is determined, but also their position is determined from these invariants. Yeah. When nu0 equals 0, we have so-called weak topological insulators, and these systems are actually can be regarded as equivalent to stacks of two-dimensional quantum spin Hall states along a stacking direction given by nu1, nu2, nu3. And in this case, because they are stacks of two-dimensional quantum spin Hall states, there will be surface states which are just an array of these critical edge states. So they exist on the side surface, but not on the top or bottom surface. And these surface states are less robust. They can be removed by, for example, dimerizing the different planes. Okay, so in order to really relate these topological invariants to electron wave functions, in general, there's a well-defined procedure, but it's complicated. Again, simplification occurs if the material has inversion symmetry. As I sort of alluded to in the band inversion theory, that when inversion symmetry is present, band inversion is described by the sign change of the Dirac mass, but the Dirac mass itself is coupled to the parity operator. So the change of the Dirac mass precisely involves a change of the parity of the occupied states. So this naturally leads one to expect that the Z2 topological invariance is related to the parity of energy bands. So the initial discovery of this formula in 2006 involves a mathematically rigorous steps, which I do not want to go through. We are physicists, so let's just accept a physicist proof. Okay. So as I said, topology change is equivalent to band inversion, which is equivalent to parity switch. So we also know that for a trivial insulator, the product of parity eigenvalue is always equal to 1. Because a trivial insulator, you can think of it as in atomic limit, then in that case, all the block states are just equivalent to localized atomic orbitals. In other words, there's no dependence of k in the band structure. Okay, nothing depends on momentum. So in that case, the parity eigenvalue at all high symmetry momentum points is always equal. So the product of parity eigenvalue at all high symmetry points is equal to +1. And so what this says, combining these two facts, it says that for a topological insulator, which is obtained from band inversion relative to a trivial insulator, it should have a parity product which is equal to -1. So this is the criterion for finding topological insulators. We need to look at the band structure of materials and take the information of band parity and take a product. So back to the example of bismuth and antimony. So these are the band parity information that's available from old band structure calculations. The plus and minus sign referring to the different parities. So likewise, S is parity even, A is parity odd. So when we do this procedure, for bismuth, the topological invariants are 0. The product of parity is +1. Whereas for antimony, the product of parity eigenvalues is -1. So this says immediately that antimony is a topological insulator, but not bismuth. Okay. So this, using this method, we also predicted other strong topological insulators, including strained mercury telluride and gray tin, which is a form of tin in diamond lattice. Okay. And this method became very handy and was now widely used in the search for topological insulator in real materials. So the experiments came about a year later from the He Hassan's group in Princeton University. So he used angle resolved photoemission spectroscopy to study the three-dimensional topological insulator compounds, bismuth and antimony. And you see that there are 5 different surface bands, which proves that the surface stays consistent odd number of Dirac points. Later, there's a much simpler compounds that everybody now works with, bismuth selenide and bismuth antimony from the Princeton group and the Stanford group. And in this case, there's a single Dirac point on the surface. So more recently, the Wurzburg group in Germany studied another material that we predicted, grade tin, which is grown on indium antimony substrate. And because of lattice mismatch, there's a strain built into the system. And the full emission result also shows a linear dispersing surface Dirac cone. So by now, there are many of these topological insulator materials, and I will just end the description of the old work here. And so, if any questions at this point? Okay, so let me continue now on to the more recent stuff. So, so the lesson we learned from topological insulator is that when symmetry is taken into account, the topological classification of phases matter becomes much richer. So one can ask the general question: are there symmetry protected topological phases beyond the Z2 topological insulators involving other symmetries? And so there's a work that you heard from Andrew Berling's talk, that's tenfold classification for topological insulators and topological Symmeters in various symmetry classes. And some of these topological Symmeters host Majorana Fermion excitations at the boundary or at the vortex core, and they can be realized using both an engineering approach involving topological insulator semiconductor hybrids, or they can be realized potentially in a new unknown symmetric materials. There is now a lot of experimental activities in this direction, and some of the beautiful work we have heard this morning come from here in Israel. And there's a different direction people are looking for interacting topological phases in boson or spin systems, such as one-dimensional Haldane chain, which was pointed out by Arisberg. And there's a lot of interest in mathematical classification of all these interacting phases, and as well as characterization of these phases through various tools, such as entanglement. And probably Liang Fu will talk about the field theory description of these interacting topological phases. So what I will do in the last, let's say, 5-10 minutes is to describe a new type of topological phases in which it's the symmetry of the crystal that is involved. So a crystal symmetry, for example, defined by the point group, is a defining property of periodic solids. And so the question then arises, are there topologically distinct phases within the same crystal structure? And again, the answer is not obvious. For example, if you look at the diamond lattice structure, as we said, the diamond, germanium, and silicon all are topologically equivalent. The electronic structure can be understood from sp3 hybridization. And so we studied this problem in 2010 using a toy model, illustrated the proof of principle that there should exist topological non-trivial phases that are protected by the crystal symmetry. Okay, so we call these phases topological crystalline insulators. These are new phases of matter that goes beyond the structure property relation. Okay, so for a given structure, there can be qualitative different phases, topologically distinct. And so last year, well, 2012, we predicted the first example of this topological crystalline insulator in real materials, the 4-6 semiconductor tin telluride. And so in this case, the tin telluride has a rock salt structure, and the topological nature of this compound actually relies on a mirror symmetry with respect to a specific mirror plane, 110. Okay. And interestingly, for other compounds in this family, for example, lead telluride, it's actually not a topological crystalline insulator. It's a trivial insulator. So once again, it's known, the reason we can make this prediction is because of the phenomenon of banding inversion known in this material class between tin telluride and lead telluride. One can make the alloy lead tin telluride, and banding inversion occurs at a critical alloy composition. The problem here is that there are 4 different points in this momentum space, the 4 L points. So banding inversion occurs simultaneously at these 4 L points, which are symmetry related. So this even number of banding inversion, according to the parity criterion, does not lead to a Z2 topological insulator in the time reversal invariant class. Okay, so this is what we concluded back in the early days, that neither tin telluride nor lead telluride is a Z2 topological insulator. The new idea now is that using a crystal symmetry, using this mirror symmetry, there is a topological distinction between tin telluride and lead telluride. Okay, so the distinction exists when the mirror symmetry is present, which is the case for these compounds. And there's a new topological invariant that I will not describe in detail, but let me just say that this new invariant, instead of being a binary number, it's actually an integer invariant. So that's why if you have 4 band inversions, they all add up to give you a topological invariance of 4, instead of being a binary number where 1 plus 1 becomes 0. So this is a fundamental reason that these materials are topological crystalline phases protected by mirror symmetry. So again, just like what I said in the case of bismuth and antimony, here we face a similar problem, which one is non-trivial, tin telluride or lead telluride. In this case, we can look at, again, the band structure of these materials. The dispersion, again, looks very similar near the band gap. Again, we have a massive Dirac fermion band structure. However, if we plot the orbital content of these wave functions, if we analyze what orbitals these wave functions correspond to, in lead telluride, all the occupied states essentially come from tellurium. Okay? This is what you expect for an ionic insulator made of lead 2 plus and tellurium 2 minus. And whenever you can deform the system to an ionic insulator, it's got to be topologically trivial. In the case of tin telluride, this is not true anymore. The occupied states in the majority part of the Brillouin zone come from tellurium, but in the vicinity of the L points, the occupied states come from tin instead of tellurium. So in this sense, tin telluride is inherently inverted. Okay. Once again, combining the low energy theory, which describes the change of topology, and with this analysis of electron wave function, we can conclude that tin telluride belongs to a topological crystalline insulator, while lead telluride is not. Okay. And this example is actually a rare example of band inversion between the cation and anions. Okay. So using ab initio calculation, we found the surface states exist on tin telluride, and they take the form of 4 Dirac points in momentum space. These Dirac points are away from the high symmetry points gamma and x, so their existence do not rely on time reversal symmetry. Even breaking time reversal symmetry, these Dirac points are still present. But instead, they are lying on a mirror plane, so breaking mirror symmetry would be able to generate a gap on these Dirac points. And you may wonder, why 4 Dirac points is topologically interesting. After all, we know that graphene, for example, has 4 Dirac points, 2 coming from the valleys, 2 coming from the spins. Or if you take an ordinary 2D raspberry electron gas, and there will be again 4 Dirac points at the Brillouin zone corners. Well, the difference here is that these Dirac points, again, have a chiral spin texture. Okay, so the spins wind around 2 pi near each Dirac point, and the winding all have the same handiness at these 4 Dirac points. So they have the same chirality. So this is the reason that the presence of such a net chirality can never be realized in a 2D system. Instead, they can only appear as a boundary on the boundary of a 3-dimensional topological crystalline insulator phase. And so shortly after our prediction, several different groups have used photon emission to study these compounds, tin telluride, lead telluride, as well as closely related compound, lead tin selenide, lead tin selenide telluride. And in the case of tin telluride, there exists linear dispersing surface states, but in lead telluride, they do not appear. And in the case of lead tin selenide, there's a very interesting topological phase transition entirely driven by temperature in the bulk. So in the high temperature phase, the band ordering is normal. We have a conventional insulator, so there's no surface states, while at the low temperature, band inversion occurs, and there exists these surface states. And one way to sort of test the symmetry protection of these surface states is to imagine what happens if the symmetry is broken. So you will hear Liang Fu talk about what happens to topological insulator surface states when you break time reversal symmetry. Here, I'll describe what happens to these topological crystalline surface states if you break the crystal symmetry. So one way of doing that is to have a structural distortion in which the tin and tellurium atom move in opposite directions. So this distortion, for example, would break this -10 mirror plane, but not the 110 mirror plane. And correspondingly, depending on basically the direction of the distortion, one can break mirror symmetry in various ways, and this will generate a mass for these surface Dirac points. both the magnitude of the mass and the sign of the Dirac mass depends on the vector of the distortion. So, my collaborator William Malhaven in Boston College got interested in these materials, and he decided to use his expertise, this STM, to study the surface states. And this is the topography image of these materials, and you see there's atomic. You see all these atoms, and because of the alloy, this is leading selenide, it looks very random. Okay, but if you take the DIDV, you see this beautiful magnetic Landau level spectrum in the presence of magnetic field, as many as 20 Landau levels was seen, and by analyzing how these Landau level energies depends on the magnetic field, one can get this plot. Okay, and so there are many interesting features in this plot, but I will only limit myself to the 3 Landau levels, okay, near the Dirac points. So there's one central Landau level whose energy does not depend on the magnetic field. This is exactly what you expect for massless Dirac fermions. So this is fine, but in addition, there are 2 additional peaks whose position, again, does not change with the magnetic field. So this causes a puzzle. So why there are additional non-dispersive peaks? And so when Vidya brought the data to us, we realized that what she saw is in fact the mass of the Dirac fermions. So this is what we theoretically expect for the Landau level spectrum of Dirac fermions. In the massless case, there is a 1-0 energy Landau level whose energy does not change with the field strength. And if you now generate a mass for 2-component Dirac fermions in 2 dimensions, there's a shifted 0 energy Landau level. Okay, so it's shifted either to the valence band edge or the conduction valence band edge, depending on the sign of the mass. But it still does not change. The position of this Landau level does not change with the magnetic field. This was actually first pointed out, at least in condensed matter context. It was actually first in the Haldane 1988 paper. And so now a coherent picture of what's happening in this material emerges. So if we have a distortion along the 110 direction, it will preserve one of the mirror symmetries, and it leaves 2 Dirac fermions massless, and it breaks the other mirror symmetry, so it generates Dirac mass. And the Dirac mass of the 2, in fact, has to be opposite because time mirror symmetry is still preserved by the distortion. So there's a plus and minus mass. And this precisely generates 3 different non-dispersive Landau levels at energy 0, at plus and minus m. And so from the experiments, we can fit with the theoretical calculation very well, and we can extract the Dirac mass about electron milli-electron volt. So this is an experiment which demonstrates the protection of the surface states by the crystal symmetry. And so experiments are still not satisfied. If there's distortion, they would like to see it. So more recently, Vidya's group improved their imaging technique. They try to literally, with STM, see the position of the atoms and average the position of the atoms within the unit cell and see what happens. And after the averaging, and you can see that the unit cell is actually distorted. It's no longer a square. It's distorted in this way, which exactly preserves one mirror symmetry, but not the other. So this provides a sort of an example where Dirac mass is generated through spontaneous symmetry breaking, similar to the Higgs phenomenon. So that's pretty much what I want to say, and let me sort of take a summary and a quick outlook. So, so this topological material is a very sort of interdisciplinary field involving theoretical physics, material science, quantum chemistry, as well as quantum information, which I didn't talk about, but you probably heard in the morning. And I think there's many open questions, many more topological materials await discovery. As Andrew said, that in the case of crystal symmetry, the crystal symmetry group is very large, and there has been now a lot of activities in trying to systematically classify these topological phases in crystalline solids. And there's a lot of interest in finding fractional topological insulators. And we are recently very intrigued by the phenomenon of interface symmetricity in these tin tera lateralized systems. And we're proposing that there may be some opportunity to realize some high temperature interface symmetricity. So lastly, let me just say that at a more philosophical level, the reason that topology can become so effective in material research, why this is the case, because we know the material research is very complicated. Right? Even for bending insulators, the bending structures are quite sophisticated. But I think what topology does is sort of a high level of abstraction. We sort of filter out all the details. Instead, we just focus on the very, very simple properties, 0 or 1, black or white, yes or no. Right? So by doing so, it really fits this philosophy of less is more, okay? As in Chinese painting, using ink and brush. So now these images, definitely do not correspond to reality. All the ratio of the size are off, but you get the main idea. Okay, so this is perhaps how topology can assist material research in the spirit of less and more. And so, again, in the same spirit, I'm not going to show you a summary again. I just say thank you. Yeah, that's right. So I should call it chiral symmetry breaking. That's probably more appropriate, yes. Yeah, chiral symmetry breaking. Actually, there is a gauge field, but the gauge field doesn't, there's an electromagnetic gauge field, right? But that is different from, that doesn't get involved, yeah. So it's actually a chiral symmetry breaking instead of a Higgs phenomenon, yeah. This talk was meant for a more general audience, so, yes. Yeah, yeah. So if you have a ferroelectric domain wall, yeah, if you have a ferroelectric domain, that's an excellent question. So if you have a ferroelectric domain wall, one should be able to see helical edge states, protected by time rule symmetry, because backscattering is forbidden, right? Because of the spin momentum locking. Yeah, but actually it depends also on the orientation of the ferroelectric polarization. If they are 90 degrees away from each other, then you will have this helical edge states. But if they're 180 degrees apart, okay, like this, then you will not.
Both thin Telluride and the lead Telluride, if they're doped, they're superconducting.
Yeah.
So does it have any interesting implications? You will go.
Yeah, that's an excellent question. So in fact, there are recent experiments by Yoichi Endo's group where they dope tin tera with indium. The phenomenon of symmetricity in indium doped tin tera was well known from before. The symmetric transition temperature can go up to around 4 Kelvin. Yeah, 4 Kelvin. Yeah, and so one might ask, is there any possibility that this gives us some topological non-trivial symmetricity, in the same spirit as copper doped bismuth selenide? So Yoichi Endo, in fact, indeed found a zero bias condensation peak, which is very robust. The height of the condensation peak is more than twice the normal state resistance. And, but again, one has to be cautious with these zero bias condensation peaks. It's seen so many places. I mean, in the case of copper doped bismuth selenide, Modi, I'm not saying anything about your experiment. In the case of copper doped bismuth selenide, there's a later STM experiment from NIST, Joe Strozier, who found the copper doped bismuth to be fully gapped. There's not any in-gap states. So, so that's why there's an open question now. What is the nature of the symmetric state in copper doped bismuth selenide? And you can ask the same question for indium doped tin telluride. Yeah. Just one minor comment. We found quite interesting this interface symmetricity. For undoped tin telluride and undoped lead telluride, these are non-symmetric. But if you make a heterostructure of the two, the interface superconducts with a TC of about 4 Kelvin. Again, this was again known from old days. Yes, so does this symmetricity has anything to do with, for example, the surface states? So this is something that we are proposing. Yeah.
Do you have any impression how to build topological insulator, let's say, like just by quantum symmetry?
And
let's say
intuition.
you're allowed to use photonic crystal.
Yeah. Oh, you mean the without spin orbit coupling?
Yeah. Well, yeah. Just
Actually, yeah, it's a good question. Sort of. Yeah. So.
clearly without T squared equals -1.
Yeah. Then actually there is a well, let me first say one fact, which is for the cases where you involve a rotation symmetry in a spinless system, one has to also worry about the symmetrical number of energy bands. Right? So it's another level of complication. You know, to what extent these classifications are robust against disorder or the existence of other bands, with a different symmetrical number. So that's more complicated. And it appears, I think actually it's quite interesting, it appears that all the robust topological phases involve, let's say, time row symmetry, which is square root of -1, or let's say mirror symmetry, which involves two-fold rotation, also square root of -1. So it appears this sort of symmetry operator square root of -1 is playing an important role in the classification.
But C2 is also square root of -1.
Yeah.
If I have spin.
C2 also generates non-trivial TCI surface states. We have a recent discussion of this in the recent paper. Yeah.
Thank you very much.
Okay.